So the point of Hess's law, of course, is to be able to predict how much energy is exchanged in a chemical reaction without actually having to measure it with a thermometer. You don't need a thermometer at all. So this is a reaction that was done by some chemist at some point in time, and this chemist figured out that it was exothermic, and it releases 390 kilojoules. Negative tells you it was released, and that the products are at a lower energy than the reactants. So if you took this minus that, gives you a negative value. Another chemist did this experiment. Took carbon monoxide, and this is what's going to be new for you guys. You can have coefficients that are fractions. Ooh. It actually is not any more scary than the stuff that we're going to be working with today. And it produces carbon dioxide, and this chemist figured out that delta H was, really exothermic. It was negative 280 kilojoules. Now we typically write kilojoules because that's a lot easier than writing negative 280,000 joules. So kilojoules is the unit of choice because joules are a small unit of energy. Now let's be smart this time. Let's actually label these with numbers. That way we know this is reaction 1, we know that this is reaction 2. Now what we're going to try and figure out is we're going to try and figure out what delta H is for this reaction without actually having to burn it. Without having to burn it, we're going to try and figure out how much energy is released when it's solid carbon and oxygen coming together to produce carbon monoxide gas. And we'll label this delta H3, and we don't know how many kilojoules it is. That's the point of using Hess's law, is if we don't know what the kilojoules is for this, we can figure it out from the previous two reactions. So now let's review some of the rules for Hess's law. There's only a couple algebra rules that we can follow. First is the rule of flipping. If you flip it, flip the sign. There's another rule that I'm going to employ, which is you can actually multiply it, which I'm going to use a time sign, times with new coefficients. So you can change the coefficients by multiplying it through by a number. I'm going to demonstrate both of these in the example problems that we're going to be working with. These are just algebra rules that you've learned in algebra anyhow. So if you flip the whole equation around, you got to change the sign on delta H. If you multiply by 1, you have to multiply by all of them. Question? Yeah.
When you say sign, you mean like the negative or the positive?
Yeah, exactly. So if I flip this whole equation over and I made it so that it was CO2 going to C and oxygen, then it would be positive 390, not negative 390. All right, so now I have to look at these two equations and figure out how I can add them up to be this equation over here. Now there's something I notice. See how this equation has carbon monoxide as a product? Neither of these two equations have carbon monoxide as a product. That's a problem. That means I'm going to have to flip one of my equations. So this top one doesn't have carbon monoxide, but this bottom one does. But carbon monoxide's a reactant, so I'm thinking I probably need to flip this so that CO is on the right side, not on the left side. So I'm going to write flip because I know I need to flip it. So I'm going to flip it, and when I flip it, I'm going to rewrite this equation just backwards. CO2 gas produces carbon monoxide gas and a half oxygen. And then my delta H, when I flipped it, is now going to be positive 280 kilojoules. And I'm going to put a single line strike through for that because I no longer want to look at it. I've now flipped it. Alright, so now carbon monoxide's a product, so if I add these two, I'm going to definitely end up with carbon monoxide on the right side. Now let's take a look at this final equation here, and I'm noticing something, and I'm like, hey, it's like a half oxygen here and a solid carbon, and there's no carbon dioxide as a reactant. In fact, there's no carbon dioxide as a product either. Carbon dioxide doesn't exist in the equation. I'm trying to add it up to equal. But do you guys see how equation 2 has carbon dioxide now as a reactant and carbon dioxide as a product in reaction number 1? So when I add these two equations together, I'm going to have carbon dioxide on the left and carbon dioxide on the right, which means they cancel out. So if you have the same thing on both the left and on the right side, then you can get rid of it. I'll show you how that also works with the oxygens in this problem as well. So what I'm going to do is I'm going to take equation 2 and equation 1, and I'm going to add them up, and I'm going to write them together on the bottom down here, which is solid carbon plus oxygen gas. So those are the reactants for equation 1. And then for equation 2, I did have carbon dioxide, right? But I already canceled that out, so I don't need to write that out. Produces carbon monoxide, CO gas, plus half of an oxygen, okay? Which is gas as well. I forgot to write that down. All right. So now you're like, oh, hey, this is pretty close to that when I add these two equations. But you're probably noticing, hey, what's with this oxygen? There's a half oxygen on the reactant side, but on this, when I add them together, I have a whole oxygen and I have a half on the right. So what I can do is I can subtract half oxygen from this side, and just like an equation in math, what you do to one side, you do to the other. So subtracting half an oxygen on that side means I have to subtract half an oxygen on that side. This goes away, and then remember, there's no number in chemistry in front of it for the coefficient. It's really just a 1, right? So 1 minus a half is equal to a half oxygen gas, solid carbon, producing carbon monoxide gas. So, hey, that adds up to this, right? That's the same thing. So that means that what I have to do is I added these two original equations together, but I had flipped number 2. So I had to flip number 2, add them together, and then I get this final one. Which means, now watch carefully, delta H3 has to be equal to delta H1 plus delta H2. So I'm going to do that math right now in my calculator. I'm going to do negative 390 plus, and remember I crossed it out because I flipped it, so it's going to be negative 390 plus 280, and I get negative 110. So I was able to predict how much energy would be released in this reaction without having to measure it, and just by using algebra. Now that's a simple one. We're going to do a much more difficult one. The much more difficult one I'm going to do for you guys is going to be it's going to be really tricky. It's going to be one where we have a lot of different reactions. So we're going to try this one out, okay? Here we go. So the new one I'm going to have you guys do is, what if I have known information about this reaction? And check it out. I've got 5 halves this time, O2. It's gas. It's really important you actually write out the states of matter for these problems. I want to pause for a second. Does anyone have any questions so far? Yes?
Why is it 5 halves, not like?
The reason it's 5 halves is that it turns out that these reactions are what we call half reactions a lot of times. And the way that we write out the equation, the only way it can be balanced is by multiplying it by 5 halves. So when I finish writing out this equation, you'll see that the number of oxygens, oops, I almost wrote it wrong, it's CO2 here, 2 CO2 gas. The only way it can be totally balanced is by having that 5 halves right there. I'm actually going to quickly rewrite this again because I felt like I did that a little sloppy. So let me do this again. So it's C2H2 gas plus 5 halves oxygen gas producing 2 carbon dioxides and water vapor. Or no, liquid water. And the delta H for this one, this is going to be my delta H1, is given to us as negative 1300 kilojoules. Then we're given a second reaction where we have solid carbon reacting with oxygen gas, producing carbon dioxide gas. And this is my second reaction, so I'm going to call it delta H2, and its delta H is negative 390 kilojoules. And then the next one, there's a third one, believe it or not, is hydrogen gas plus 1/2 oxygen gas, producing liquid water. And its delta H, we're going to call this delta H3 because it's our third reaction, is equal to negative 290 kilojoules. Okay, so I've got 3 equations. It's starting to look a little funky. I'm going to put a box below it because what we want to do is we want to figure out delta H4 in kilojoules for this reaction. And the reaction we want to figure it for is 2 carbon solid plus hydrogen gas producing C2H2 gas. All right, when I look at this, I'm going, all right, wow, this is a lot to wrap my head around. I'm going to give you guys, I'm actually going to pause this recording temporarily, and I'm going to give you guys a second to talk with your neighbors and make a plan about how you are going to rearrange these equations so that when you add them up, you get delta H4. Remember, we can only do this by having delta H4 being added up, delta H1, delta H2, delta H3. So I'm pausing my recording. I want you guys... Alright, so here we go. Now that you guys have attempted this quite a bit, the first step you should have recognized is that you need to flip this equation. The reason you need to flip that equation is because we need C2H2 to be a product, not as a reactant. So when I look at it like that, I'm like, all right, I'm going to flip it. So it's now going to be 2CO2 gas plus liquid water produces C2H2 gas and 5/2 oxygen. And then I might as well cross this out and then just make this positive because I flipped it. Remember, if you flip the equation, you got to flip the sign. All right, now I'm looking at it again. Now, I'm imagining in my head, I'm like, all right, if I add these three equations together, then what am I going to get? Well, the liquid waters are going to go away because I have liquid water as a reactant and liquid water as a product. What else have I got? I got...
You can subtract.
I'm looking at, right now, what I'm doing in my head is I'm doing the things that you should be doing, which is noticing, hey, do you guys notice that there's absolutely no oxygen in this equation right here? Also, do you guys notice that it says 2 carbon? See how it says only 1 carbon up here? Shouldn't we make this 2 carbon? Yeah. So let's make it 2 carbon. Now watch how I do this. Watch. I figured this out by looking at the carbon and I'm like, all right, it's 2 C's. I need to make this 2 C's. So I'm going to multiply this by 2. But if I multiply this by 2, I have to multiply everything else including my negative 390. So it's now 2O2 and 2CO2. And then when I look at it that way, now I have to multiply this by 2. So it's now like negative 780, right? So negative 780 kilojoules. Okay, so I've done that. Now I notice something else convenient. Do you guys see how it worked out that once I multiplied this to make the 2 carbons, I also have 2 carbon dioxides on the right, and that's going to cancel out the 2 carbon dioxides over here. So let's imagine adding all 3 of these equations together. So I have 2 carbon dioxides on the left, 2 carbon dioxides on the right. When I add them together, it's like a spectator ion. It's going to be the same on the left as it is on the right. So that's going to go away. The liquid water's on the left, the liquid water's on the right, and they're the same amounts. That's going to go away. But the oxygens, that becomes tricky. Guys, this is 2. This is 1/2. What's 2 plus 1/2? 2.5, right? So isn't 2.5 the same as 5/2? Yeah, because here, let's do some basic old school math. Like, you know, the old trick, 2.5, 2 times 2 is 4 plus 1 is 5/2. So yeah, so this adds up to this to be 5/2, which means they go away. So my equation is set up. If I add all 3 of these delta H's now, I'm going to get this equation down here. 2 C's plus H2 produces C2H2. So the math that I'm going to do for delta H4 is going to be positive 1,300 kilojoules plus negative 780 kilojoules plus negative 290 kilojoules. And then the answer you get after you add all 3 of those numbers together is you get the final answer, which is positive 230.
Mm-hmm.
So delta H4 for the reaction we're trying to find is positive 230 kilojoules. Okay, now, I spent quite a bit of time teaching you how to use Hess's law. That's about as hard as it will ever get. But we've got a problem here. In an AP class, there's so much content, and in a college class, there's so much content, it's impossible for your teacher to teach all the stuff that you need to know how to do. So we're going to see if you guys can extend yourself to be able to teach yourself how to do the same thing, which is predict delta H for a reaction that you don't measure by burning anything, but using a different method called enthalpies of formation. We're going to be using the AP chemistry textbook so you see what a college text is like. It's literally, if you don't take AP Chemistry this year, but you have to take a chemistry class because you're interested in